Welcome to this explainer. It's kind of wild, but most laboratory accidents, they aren't caused by those massive Hollywood-style chemical explosions. Nope, it's usually simple stuff, unwashed tools and messy desks. So today, I want you to step into a totally new role. Imagine you're not just a grade 7 scientist, but the lead safety inspector stepping into a highly active laboratory. Your eyes are your absolute best tools, and your primary goal is to ensure the integrity of the science and the physical safety of everyone in the room. We're going to master the essentials of laboratory work, breaking down the exact tools you need and the critical safety habits that literally separate a true scientist from an amateur. All right, let's dive into this. So there's this golden rule in science. The lab is not finished when the experiment ends. It is finished when the room is clean. Honestly, this mindset is a real game changer. Lab safety and etiquette aren't just a list of arbitrary rules you memorize to pass a test. They're an ethical responsibility to a shared ecosystem. If you leave a messy station behind, or say you fail to clean a spatula before the next group tags in, you aren't just breaking a rule, you are actively ruining the data of your classmates. Your mindfulness directly impacts everyone else's success. Here is our quick roadmap for today's explainer. First, the ethical mindset. Second, the laboratory tool matrix. Third, the RAMP framework. And finally, spatial awareness. Section 1. The ethical mindset and your responsibility as a scientist. When you step into the lab, you're agreeing to a social contract where every action has to be deliberate. Moving right along to Section 2, the laboratory tool matrix, where we categorize equipment into 4 functional families to ensure precision. Let's dive into the measuring category and look at a comparison that really nails why specific tools matter. First up is the graduated cylinder. It's a tall, narrow container with markings used to measure volume incredibly precisely. But to use it right, you've got to get right down to eye level and read the bottom of the meniscus. You know that little downward dip in the liquid? Compare that to the burette. While a graduated cylinder measures what's already sitting inside it, a burette is uniquely designed for titration processes. That means it measures the exact volume of a liquid as you're actively adding it to a solution. You would absolutely never use a standard beaker when you need this level of critical accuracy. Now, looking at the mixing and containing family, there's a really crucial distinction. The standard beaker is awesome for transporting, heating, and storing substances, for sure. But for accurate volume measurements, it's entirely unreliable. On the flip side, check out the Erlenmeyer Flask. It has this broad, flat base that tapers upward into a narrow neck, and that design is super intentional. It lets you mix liquids by aggressively swirling them around without the risk of splashing dangerous chemicals all over your workspace. Pretty brilliant, right? Next up is thermal and heating. A Bunsen burner gives you this intense open flame that is absolutely perfect for combustion. But to use it safely, experts rely on a mental, step-by-step checklist called the Set Alight mnemonic. Basically, you ensure the area is safe, check your equipment, turn on the gas, and light it from the side, among a few other key steps. It's a structured little ritual that literally prevents disaster. But hey, what if you have a highly flammable substance or you need to heat something incredibly slowly? Well, that's when you swap the flame for a hot plate. It's an electrically powered flat surface designed for gentle, controlled heating. Knowing exactly when to use an open flame versus a hot plate is just a fundamental safety skill. Finally, we've got the handling and supporting category. I mean, you can't exactly hold a boiling test tube over a Bunsen burner with your bare hands, right? No way. Tools like the ring stand and universal clamp are absolute lifesavers here. You've got this heavy metal base with a vertical rod, which lets you securely connect clamps to suspend your glassware, like a flask or a burette, at a specific height right over your heat source. It keeps your hand safely out of the way and keeps the whole shebang perfectly stable during a volatile reaction. All right, now that we know our tools, let's hit Section 3, the RAMP framework. This is a comprehensive risk management system created by the American Chemical Society. Let's break this acronym down step by step. Number 1, recognize the hazards before you even touch a piece of equipment. Like, is that glass cracked? Number 2, assess the risks. What could actually go wrong here? Are we dealing with a mild spill or a full-on chemical fire? Number 3, minimize the risks. This means gearing up with safety equipment and setting up those ring stands securely. And number 4, prepare for emergencies. You literally need to know exactly what the fire extinguisher and eye wash stations are located the second you walk into the room, and exactly how to use them. So what does RAMP actually look like in practice? Well, it looks like a lab in motion. Students actively protecting their eyes with safety goggles, throwing on lab coats to keep hazardous spills from ruining their clothes, and keeping food and drinks completely out of the workspace.
They are following instructions, disposing of waste in the designated containers, and, this is a huge one, never ever tasting or sniffing chemicals directly. If you need to smell a substance, you gently waft the fumes toward your nose. You never put your face directly over a beaker. That right there, that's RAMP, minimizing risks in real time.
Which brings us to our final section, spatial awareness and navigating the shared laboratory. It's a highly active, crowded environment.
The absolute crucial point here is understanding the severe hazards of poor spatial awareness. Think about the chain reaction. If you engage in horseplay or just make a sudden, careless movement, you risk knocking over a flask filled with an unknown liquid, and that spill can easily hit a classmate. If you lean directly over a heated crucible with bad posture, you're inhaling toxic fumes. If your group is rushing and leaves an unwashed spatula behind, you cross-contaminate the next group's materials and completely ruin their data. And if you ignore a tiny hairline crack in a glass beaker before heating it on a wire gauze, the thermal stress will literally cause it to shatter violently. This is exactly why running and sudden movements are strictly prohibited.
Which leaves us with this final, really vital question to reflect on. How does maintaining spatial awareness actually prevent catastrophic accidents? Really think about it for a second. When you're constantly aware of your physical posture, the tool accuracy, the sharp instruments in your hands, and the people working shoulder to shoulder with you, you aren't just blindly following rules. You are actively protecting the integrity of the scientific data and the physical safety of your entire classroom. Remember, you are the lead safety inspector of your own station, and until that station is perfectly clean and safe, the experiment simply isn't finished. Thanks for joining me on this explainer, and I'll catch you next time.